I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. I want to make a short video looking at a very simple concept, one that we feel like we probably don't even need a video on. What's the pH of water? So we know it's a pH 7. We're done, right? Actually, to a lot of people's surprise, even over what I would call physiological conditions, the pH varies significantly away from pH 7. And I've taken this from Tinoco's book in Physical Chemistry, Principles and Applications in Biological Sciences. So this has been used in the past for BCH 341, which is a physical chemistry with a biological focus at ASU. He does an extremely nice job, the authors, in chapter 4 of their book, looking at just this question. So I'm drawing from some material out of this book for this video today. So one of the tables, and this would be common in any physical chemistry book you look up anywhere, where you often look up a series of pKa values, for example, for a bunch of different, any acid-base equilibria, right? Like you're going to look up equilibrium constants, any type of reaction. And when you see water, you see exactly kind of what you expect. Okay, a pK of 14, right? Like a pKa value, right? We know, it's acid-base chemistry. This is kind of at the heart of what we think of as forming, protons, H pluses, acids, and OH minuses for basic, etc. And the equilibrium of water. You can also, for any of these, look up, and it's often given the ionization enthalpies. And usually it's, of course, under standard state conditions. So standard pressure and temperature of 25 degrees Celsius. And you look that up and you see a value of 55 kilojoules per mole. And so when we look at that, the way we often look at this is it's 55 kilojoules per mole. And how is this obtained experimentally? Well, it's obtained by looking at the concentrations of protons, or H plus, and OH minus, water, right, in other words, the equilibrium constant, as a function of, and we usually plot it as the inverse temperature. And so this is going, so this is cold, and this is hot, right? So the opposite direction that we're used to seeing it, right? And this is probably, if I remember my math very well, this is probably on the order of one inverse, so around 60 degrees Celsius. Less than zero, probably about minus 10 degrees Celsius or so, just to give you kind of some temperature ranges. This goes so a little below freezing, to below boiling, right? But we're looking at it, and you can see, the equilibrium, this is on a log scale, changes significantly over this temperature range, and that's what allows us with the Van Hoff equation to get at a delta H for this ionization, for the reaction of liquid water going to H plus in aqueous solution plus OH minus in aqueous solution, right? And that's the delta H that we're looking at for that. So it's telling us that this is endothermic, right? That it requires heat to make this ionization, which seems about right if we think of another, what I would say, common thing, which is if you take kind of a strong acid, the most common, like something like HCl, strong base, something like sodium hydroxide, lye, right? You combine these two things together, you get salt, NaCl, and water, right? But we all just know from experience, if you do this, if you take lye, a strong base, and acid, it's very, heat is generated. The container gets very hot. It's very exothermic, right? When you take two ions to produce, water. So it's not then surprising when you think of it from that standpoint that the opposite, taking water and forming ions, is endothermic, right? So, but it also, because of this, you can see that over a range, that we're often looking at, this is in the range that we often look at, the equilibrium shifts a fair amount, and it does so, in a sense, based on Van Hoff's equation. We're looking at this at constant pressure, right? Shown here. And so how would we look at this? Well, we said that, we're going to say that this is the change in the equilibrium coefficient and we'll integrate over this from, equilibrium 1 to equilibrium 2, right? It's minus this ionization. But it can be, the nice thing, the Van Hoff equation is for any chemical reaction. So you can write as a general chemical reaction, it's general standard state over R. And then this will be integrated over from T2 to T1 of D1 on T, right? We'll get that ln of K2 over K1 is equal to minus the delta R, we're looking at the ionization, over 1 on T2 minus 1 on T1. Right. So say, for example, we want to know the pH of water at physiological temperature or body temperature, which is 37 degrees Celsius, right, in this case. So we know, K1, we know the equilibrium constant, at 298. We know our final temperature, 310 Kelvin. We knew our initial temperature, 298, which is the standard state, right? We know the gas constant is 8.3 joule per k-mole. And we know the delta H from this fit of 55.76 kilojoules per mole. So we can solve, in a sense, for K2 in this case. And what we'll find is that we'll get a K2 if we do this for 37 of 2.4 times 10 to the minus 14. So it's not 1 times 10 to the minus 14, which is K1, what we started at. It changed some. And so now let's get this, though, in terms of not the equilibrium, which maybe we don't, even if we put this as pK, we might not have as much of a sense for, right, as, what the pH is. So in this case, this reaction is, we know that it's the concentration of H plus and OH minus that gives this K2, this equilibrium constant K2, which we said is 2.4 times 10 to the minus 14, right? Because of the reaction, it's water going to form equimolar, we can say that this is the same as the concentration of H plus, times the concentration of H plus or H plus squared, right? Because this has to equal that amount, right? So in a sense, this is just starting, knowing that our reaction is water to form these two ions, right? So now, in a sense, we can just take the square root of this number. So we can, take the square root of this, of K2, to get our hydrogen ion concentration, and we can take minus the log base 10, of the hydrogen ion concentration is defined to be pH, and we'll get a value of about 6.8. So unlike at standard where we have, a pH of 7, it's deviated 0.2 units from that. So what I would encourage you to do is look at this at several different temperatures, kind of in this physiological range, as high as, under the boiling point, so something, less than 100 degrees Celsius, and, even you can go a little lower than the melting point, because you can supercool water significantly into the liquid state, 30, 40 degrees oftentimes before you hit the homogeneous nucleation point. So I hope this very simple question, which is what is the pH of water, and that you can see that it has a significant temperature dependence, will help you in seeing some basics about equilibrium and how thermodynamics can really help understand even some of the simplest problems. Thank you.